Hello, math humans. We're going to do 1.5 today. We're going to be talking about limits at infinity. Our objectives are that we're going to determine the limits at vertical asymptotes and then as a function approaches positive and negative infinity. So to remember, a limit exists, a limit approaches a value if and only if the right and left hand limits both agree. And then one-sided limits are if we consider the limit from only one side. So let's just start with an example. So this says find the limit as x approaches 1 of 1 over x minus 1 squared. So right off the bat, you should notice that I have a vertical asymptote at x is equal to 1. You should also notice that this is the indeterminate form because the world explodes if you substitute a 1 into the denominator. So I have nothing in the numerator, and I'm going to graph this just because sometimes graphing is helpful for my little brain. So here's a 1. There's my vertical asymptote, and this particular graph is going to do this. Okay? Well, if I look at the limit as x approaches 1 from the left of the function, it's going to approach positive infinity. And the limit as x approaches 1 from the right is also going to be positive infinity. Now remember, this is that technical case. The left and the right-hand limits agree, but this particular function increases without bound, which means that it continues forever up, which means also that therefore the limit of f of x as x approaches 1 does not exist. And this is kind of an interesting situation in your book. The book will tell you that the limit exists and that the limit is infinity, but when you take your AP exam, because the function increases or decreases without bound, that means that there's nothing to put a boundary on the function. Therefore, there is no limit to the function. So the appropriate answer is does not exist. Now, if we look at this also, this is another way of confirming that I have an asymptote at a particular constant. If the limit approaches plus or minus infinity, they both don't have to equal the same thing, then that can confirm with calculus that there is actually a vertical asymptote because the limit would not exist. All right, let's do your second example. I think I say that a lot. And I want to find the limit as x approaches 1 of a negative 1 over x minus 1. Again, I have a vertical asymptote at x is equal to 1, and it is the indeterminate form for the limit. And I'm going to sketch my graph. This is a negative 1, so here's my 1, and there's my vertical asymptote. Because this is a negative 1, that means that my branches have been reflected. And notice that the limit of the function as x approaches 1 from the left is positive infinity, and then the limit of the function as x approaches 1 from the right is negative infinity. Even from just the definition of a limit, the two limits don't agree, therefore we can say that the limit of the function as x approaches 1 does not exist. Okay? This also confirms that this particular function has an asymptote at x is equal to 1 because the limit did not exist. All right, let me turn our pages. Okay. All right. Example number 3. I want to find the limit as x approaches 1 of x squared minus 3x over x minus 1. So I do notice that I have the indeterminate form, so it means I need to do some math, right? Because if I tried to take the limit directly, I would get a 0 in the denominator, so the world would explode. I'm going to factor, so this is the limit as x approaches 1 of x times x minus 3 over x minus 1. Now let's go back and talk about rational functions for a moment. Remember that in a rational function, the numerator is actually going to give you the zeros, the denominator gives you the vertical asymptotes, and then top to bottom gives you the horizontal asymptotes, okay? So I know that I have a vertical asymptote at x is equal to 1, alrighty? The degree is higher in the numerator, so that means that I'm going to have a slant asymptote, and it's basically going to be y is equal to x, okay? It doesn't matter what else goes with it, this is what's important. So now let's sketch the graph. I had a vertical asymptote at 1. I guess I should put the 1 over there so my little dashes can get in there. I have a slant asymptote at y is equal to x. I have an x-intercept at 3. That's coming from the numerator. And then I actually have one at 0. So my slant asymptote probably has like a -1 in it or something so that it's not right there. So I'm just going to scoochy it down a little bit. Okay. So then my curve is going to cross here, and then my curve is going to cross here at 0. Okay, so we'll draw it like that. It's a bummer about drafting in pen because it's hard to erase. So now here's what I want to think about. So this is as x approaches 1. Okay, sorry, really crappy graph. My graph is going to go that way, and we'll just pretend that that's not there, because I'm going to say my limit's not working. So my limit of the function as x approaches 1, and let's do from the left, is going to go up to positive infinity, and then the limit of the function as x approaches 1 from the right is going to go to negative infinity, and then I can say, therefore, the limit of the function as x approaches 1 does not exist. Okay, sorry, I was thinking ahead about what happens at infinity. Alrighty, so let's move and do our next example. So we're going to do example 4. And it says, find the vertical asymptote. My daughter tells me I butcher that word, so I'm sorry. Verify using a limit. That must be the difference between an engineer and a mathematician. All right, so h of x is equal to x squared minus 4 over x cubed plus 2x squared plus x plus 2. All righty, so my favorite F word is factoring, so I'm just going to factor all over the place. So the numerator is x plus 2 and x minus 2. The denominator, I'm going to do some grouping. I'm going to take out an x squared and I get x plus 2, and then I have an x plus 2, and then I have an x plus 2 in common, and I get x squared plus 1. All right, so I'm going to write x plus 2 and x squared plus 1. This is irreducible over the reals. If you'll remember from pre-calc, that means that if I solved for x, I would get an imaginary number, so therefore this is not a vertical asymptote. That's going to cancel. It's removable, so I have a hole at x is equal to a -2. Okay? All right. So now that I know that, I know I don't have any vertical asymptotes. I know that I have a hole at x is equal to a -2. And so now what I'm going to do is I'm going to look at the limit as I approach the hole. So technically it's not a vertical asymptote, but we're going to use our appropriate math words. So I'm going to take the limit of h of x as x approaches a -2. And because my function is this, I can do direct substitution. So I'm going to get a -2 minus 2 over a -2 squared plus 1. So this is a -4 over 5. So then the limit of h of x as x approaches a -2 is a -4/5. So unlike the vertical asymptotes where the limit didn't exist. In this situation, the limit does exist, which verifies the whole. So I would say when it says find the vertical asymptote, I would say f of x has removable discontinuity at x is equal to a negative 2. Therefore, no vertical asymptotes. Okay? And then it says verify using a limit. My limit is here. And so now I have made a simple and concise statement. Alrighty, that is it for today. I will see you soon.